Hi guys, welcome to chapter 12 of database internals. So I'm Amaka and I'm going to be taking chapter 12. So today we're going to be focusing on anti-entropy and dissemination. Today's topic focuses on data propagation within a cluster system. Um, Next slide, please. Okay, so entropy is the measure of degree of disorder in a system. In the context of distributed system, it's the degree of state divergence between replica nodes. Typically, the aim is to keep the level of entropy as low as possible to have a properly functioning system. So we make use of anti-entropy mechanisms to identify replica nodes that have inconsistent data and reconcile them. So data inconsistencies can come from, frequently deleted data or node failures. So anti-entropy mechanisms help with that. So to keep nodes in sync, so to keep replica nodes in sync, anti-entropy usually has either a background or a foreground process running. So the background processes typically use measures like Merkle trees and update logs to detect divergence, while the foreground processes use measures like hinted handoff and grid repairs. So we'll cover all of this in the later slides. Please feel free to ask any questions at this point. Next slide, please. Okay, so we're going to focus on read repairs. Sorry, can you go back? I think you missed the slide. Yes, so read repair rather is an anti-entropy mechanism that detects divergence. Um, so the way it works, right? When you have a coordinator node and then you have other replica nodes. So when the coordinator node performs a distributed read, it optimistically assumes that the replicas are in sync with, the same information, right? But if that's not the case, and some replicas send different responses when they're queried, the coordinator node takes note of that and then sends the missing updates to these replicas. So one thing to note is that some databases bypass, contacting all of the replicas in the nodes, right? And instead make use of tunable consistency levels. So the idea is there is a configurable consistency level, right? And if there are a given number of nodes that satisfy these levels, then the system is good to go. Next slide, please. So read repairs can be implemented in two ways. So you have the asynchronous read repair, you have in read repairs. So when a read repair is set to blocking, the read repairs blocks write sent to other replicas until the response has been reached. For asynchronous read repairs, right, tasks are just simply scheduled to be executed after the results are returned to the users. But one advantage of blocking read repairs is they provide read mono monotonicity, right? But they're usually not optimal for data availability. So when it comes to optimizations, right, some databases use specialized iterators together with merge listeners to fast track read repairs. So these iterators, reconstruct the differences between the merge result and the individual inputs. And the coordinator node uses this to notify other replicas about missing updates. Yeah, I hope I'm not going to pass yet. Next slide. If anyone has questions. Okay, so digest reads. So digest reads is an anti-entropy mechanism where instead of issuing, full reads to each replica node, the coordinator node issues one full read and then sends out digest reads to the other replicas. Um, so the coordinator node, so the digest requests work by reading the local data of a replica, and instead of returning a full snapshot of the data that's been requested, it computes a hash and returns it. So the coordinator node takes the hash, computes it, and compares it to the digest read results of all the other replica nodes. So if the replicas match, like if the hashes match, then they're in sync. But if that's not the case, so because the coordinator node has no way of knowing which replicas are ahead or behind, so if there is no match, right, the coordinator node then issues a full read to the replicas that have no match. So basically bringing the other replicas that have no match up to speed. So digest reads are they're typically computed using a non-cryptographic hash function like MD5. Next slide, please. So we're going to take a look at hinted handoff. So this is another anti-entropy approach, but it works for right side repairs as opposed to read repairs. So this works. So this works when the coordinator node sends a write to the target node, right? So if the target node does not acknowledge the write sent by the coordinator node, maybe due to a node failure, the writer coordinator, stores a special record. And in the metadata, then when the node gets back up, sends back that hint to the target node so that it can have all of the missing updates. So optimizations for this, some databases like RAC use sloppy quorums with hinted handoff. So when a replica failure happens, the held nodes are used instead as a backup. So we have an example. So if we have a 5 cluster node where A, B, and C, so we have a 5 cluster node A to E, where A, B, and C are replicas for the write operations. If we have node B and node B is down, and node A is the coordinator node, the right coordinator node, A can send data to node D instead, but it sends the data along with a hint that it stores in its metadata, right? So once node B gets it up and running, node D node D sends the data back to node B, right? And node B replays all of the data. So um, once node B has recovered the full data, node D can be safely removed. Next slide, please. So we're going to take a look at Merkle trees. So for read repairs, right? Read repairs are best for currently queried data, while Merkle trees are usually used to detect inconsistencies on data that's not actively queried. So Merkle trees make use of a compact hash representation of the local replica data. So it basically uses a hash tree, or it basically returns a hash tree. So this hash tree is hierarchical in nature, right? But the way this hash tree works is the lower level nodes, so nodes that do not have children, store the hashed data of the replica local data, while the non-leaf nodes, so the nodes that are basically parents, store the hashes of their child nodes. So a lot of databases use Merkle trees to reduce the cost of reconciliation. But one thing to note is that, sorry, can you go to the next slide? So one thing to note is that Merkle trees get computed. So they use recursion. So they use recursion from bottom to top. So this means that if there is a change in the data, it triggers a recomputation of the current subtree. Yeah, so there's also the trade-off between the size of a tree and its precision. So precision in terms of how small and exact the data ranges are. Next slide. Yes, please.
I actually have a question here, and I mean, this is for everyone, if you've thought about it. I wonder whether Merkle trees are like overlaid on top of B plus trees, or if, like in a database, would they be like a separate thing altogether, or would they kind of be overlaid on top of like a B plus tree? I don't know if anyone has thought about that, but yeah. Okay. We can leave the question then. But yes, I guess something to think about might be interesting. Yeah. All right.
Yeah. But thank you. Yeah, so we can go to the next slide. Yeah, so we have the bitmap version vectors. This is another approach, right? But this resolves data conflicts based on recency. So in this, with this approach, right, each node keeps a pair log of operations that happened locally or that gets replicated, and the logs are compared, right? So if there is a missing data, then missing data is replicated to the target node. So one interesting thing about, one thing I found interesting anyway about bitmap version vectors is that it makes use of a logical clock, right, to track replica state. I think this is the only approach that does that. All other approaches use different mechanisms to detect inconsistent data. Next slide. So this is my favorite concept in this chapter, gossip dissemination. So it's a really interesting concept because it's modeled after the way rumors and diseases are spread in society. So the idea is that diseases spread, like diseases are passed from one person to another until the population dies out. And rumors are spread because people are still interested in hearing them. So the way this is being mapped in this context is gossip dissemination works by, using cooperative propagation to spread information from one node to the rest of the cluster, right? So as long as they are missing data, right, that propagation is going to take place. So as the information spreads, right, the scope increases, more processes become involved until the final node has like the exact replica of the data that it needs to have, then the process gets terminated. So an advantage of this is it helps with high reliability in the presence of system failures. It helps systems it helps systems failure adaptability in systems. So messages are not sequential; they are being propagated in a very random manner, right? So which means if communication between components fail, delivery can still happen. So this is useful for asynchronous message delivery in decentralized systems. So recursive dissemination, right? There are two ways we can look at processes in recursive dissemination. There is sorry, I didn't take that diagram off. I was supposed to take it off. So there are two ways we can look at processes in gossip dissemination. There is the infective process, and then there is a susceptible process, right? So all processes start in a susceptible state before they get infected. So infective processes are processes that hold records that are supposed to be spread, that hold data that's supposed to be spread to the other nodes, while the successful processes are processes that are yet to receive this data. So typically, when an update for a data record arrives, the process that receives the updated versions becomes an infected process, and then it starts propagating that data to the rest of the nodes. So until a node has received an updated data, it is in a successful state, but after receiving the data, it moves from that to an infective state. Next slide, please. Yes, so an optimization here is that I found really interesting is gossip dissemination makes use of a loss of interest algorithm. So this algorithm basically checks for how quickly a node can receive updates, and it also tries to reduce the rate of message redundancy to a very, very low level. So sorry, I'm trying to gather my thoughts. So this is also useful for systems that have flexible node membership or mesh networks. Yeah. Next slide. Okay.
So I was actually thinking about this, and I actually have a question mark there. So does anyone know why the optimization of, sorry, give me a sec. Sorry. I can't remember what his name is in the note again, but there's a part in this book that says that because like gossip protocols don't require coordination, they are useful for systems with flexible membership, right? Something like that. So
Yeah.
why is that? Like, has anyone thought about that? Is it because like coordination forces, like if coordination occurs, does that mean that nodes cannot freely leave or like enter or join rather a cluster? I didn't really follow that. So yeah, Damon.
Yeah, I think it makes sense because if you have a coordinator, so for example, I think in Kafka they have something called a broker, and then you have the consumers. So the brokers have to kind of like register with the broker. I mean, the consumers have to register with the broker to join, like a consumer group, and then so the broker has an idea of what the consumers that are, consuming a particular topic. So I think when you have a coordinator, the membership is the coordinator has to be informed for a node to be part of the network. But in a gossip protocol, something like cryptocurrencies, like Bitcoin, for example, it's flexible, right? There's no coordinator. It's just a bunch of every node just somehow gets a list of peers, and then you start using some form of P2P and gossip protocol to get like an idea of what the ledgers are, in the network, keep up to date with what's going on in the Bitcoin network. So and that's the whole idea behind Bitcoin. We don't want to censor nodes. We don't want some form of like membership because coordinator in that kind of network. Because if you once you have a coordinator, it defeats the purpose. Yeah, so I think it makes sense that if you look at it that way. So membership is flexible, or there's really no concept of membership. Anyone can just join the network. Yeah.
Yeah, that makes sense. And I guess like if like you have to register with the coordinator, then it also makes sense that like propagating messages has like a higher overhead if like the registrations and deregistrations happen frequently. So yeah, that makes sense. Amaka, you can continue. You also raised your hand. I don't know if Rosa raised it.
Yeah, I have a question for Dami. So based on what you've said, what happens in the event of a node failure? Because I know coordinators like usually have a way of attending to that. So if there is no coordinator node, what happens when a node failure?
Oh, you mean if the coordinator node goes down?
No, not the coordinator node, like a random node failure.
I think this question is about when there is no coordinator dummy. But I mean, sorry, I kind of want to set the field. When the way coordinators usually check if their nodes are still reachable is by doing health checks, by the way. So yeah. So I know that was one question. But for system without coordinators, dummy, I think that was the question. So you can answer that one. So if a node fails in a system without a coordinator, how do we know that?
Yeah, I think it was covered in one of the chapters. If I remember correctly, when nodes try to communicate with, let's say they have a list of peers that they frequently communicate with in the network. I mean, if you don't get any response from a particular node, it's a way to kind of add that node to some form of list, like a list where okay, these are nodes that's probably dead, or there's some network partition issues with that node. Yeah, I think that's what happened in a system where there's no coordinator. And then if there's a coordinator, like you said, there will be some form of health check that the coordinator does. Or I think it's either the nodes have to send some form of heartbeat to the coordinator. I think that's how it works in Kafka as well. So that way the coordinator knows that the node is still alive. And if it doesn't get that beat within a particular threshold, it marks that as a dead node. Yeah, that's what but I remember there was a chapter that covered how nodes in this kind of system where there's no coordinator can, kind of detect when their peer is down, and they just kind of add that to a list and, ignore it and don't work with other peers. Yeah.
Yeah, that makes sense. Thank you, Dami. Okay, please coming back to the next slide. Yes, so we have gossip mechanics. So this makes use of a configurable parameter called funnel to periodically select pairs. So the selection is sorry. Yes, so fan out is being used it goes hand in hand with latency, but it depends also on the size of the system. So in this context, right, whenever a process learns about a new piece of information from its peers, right, it will attempt to pass it on further. Sorry, this part really confused me a bit, so I might not really dwell on it. But
It's
this was
fine.
what I was able to elaborate.
I mean, I can try to add some context. So, fan out is essentially how many nodes can one node send messages to? I guess in this context, it's like, so if you have a gossip protocol, the higher the number of nodes you can send a message to, the faster the whole cluster will get the message, or the gossip, whatever. So fan out is the number of nodes that each node essentially can send to. The probabilistic way of choosing pairs, I guess like that would be an implementation detail, but the idea there is that a node would have a group of pairs that it can send to. And maybe like this group of pairs can change, like depending on some factors, like so whatever the factors are, that would be an implementation detail. So if a group of nodes send messages to another group of nodes, there is a potential that like there are multiple nodes that are sending to some of the same nodes, right? Especially because like pairs are chosen probabilistically, like we're not the ones deciding. So it's possible that two nodes can have some of the same nodes. So that is where the overlapping message redundancy comes in. So one node can send the message to another node, and someone else can send the message to the same node. And then there is redundancy. In general, in gossip protocols, we want to try and reduce the amount of redundancy throughout the system, so that we're not doing more work than we need to. The fan out and latency depend on the size of the system. So fan outs, again, like the number of nodes that you need to send to would depend on how big the network is or how big the cluster is. The latency here being, at which point do you like, I know there were two separations made in the book. So there was one for reaching convergence, which I think is at the point, and then there was another for making sure messages have gotten to all pairs. So it is possible that messages have gotten to all pairs, but the network has not reached convergence. Like what? Yeah. So that is why we try to reduce the amount of redundancy, right? So if you can reduce the amount of redundancy, then you have a closer the time between convergence and the time between when pairs get all the messages is kind of closer. So if there's a lot of redundancy in your system, then there's like that is more disparate. So yeah, you can see like a wide difference. But essentially, latency is how much time does it take from the time I start this gossip protocol or gossip algorithm, whatever, to my system reaching convergence. And the bigger the system is, the bigger the cluster is, the longer that takes. So yeah, I don't know. I hope that's clear, but that's yeah.
Yeah, it is. Okay, does anyone have any questions? Yeah, okay. Next slide, please. Yes, so this is overlay networks. Typically, they act as a middle ground between message optimization and maintaining redundant connections. So this is, yeah, so nodes in the system form spanning trees. So they are unidirectional. There is no loop, but these are graphs, right? They have these distinct edges. So the idea is to get the messages delivered in a fixed number of steps. So that's the method optimization part, and also maintain really low redundancy. So an optimization here is to allow quick recovery from connectivity loss. We can make use of a fixed topology and a tree-based broadcast approach. Here, this is unclear to me. The book did not explain further. Yes, so if that's not the case, then a fallback to gossip protocols can be used for system recovery. Potential downsides. So there's a high possibility of pairs coming together to form in an interconnected island. I don't know what's the side effect of that. Yeah.
Okay. I don't know if anyone else wants to comment on this. I have an idea for what this is saying, but yes, Ugochukwu.
Okay, so can you hear me first?
Yes.
All right. So first off, I wanted to comment on the question asked earlier about in a bit of a noisy environment about how failure is detected in a system where there is no coordinator. So like Dami already said, there was a chapter that discussed that, but there are a couple of ways. The first one is heartbeats and pings, sorry. So each of them basically check themselves every once in a while to ensure everybody's still online. So if one is not online, then maybe the one who detected it is no longer online could send a message to others to let them know that one of them is no longer online. There was also a sort of similar algorithm on gossip. So they actually gossip against each other, just like the way they gossip here. They tell the ones around them. So let's say we have P1 up to P5, and P1 notices that maybe P2 is not available. It can tell the nodes in its own fan out that P2 is not available. So maybe those ones should try and they sort of figure out how to resolve it, and then maybe bring up a new node or something like that. And then there's also a probabilistic way of measuring it, the Phi-Acurial system, whereby they also send hard bits, but if they notice or they try to send a message to a particular node and the node is not responding, they increase the probability that node, they have like an amount that they know as the threshold that if it passes this, so let's say they're taking in percentages, maybe if it gets to 70%, this node is no longer active. So just treat it as a failed or a dead node and try and bring up a new one. So they would basically try to send messages to the node, and if they notice the node is not active or didn't receive the message, maybe didn't acknowledge it, they would increase the factor of the probability of it being down by a particular factor, rather. So they would increase the probability of it being down by a particular factor. And when it gets to a particular threshold, they inform others that this node is probably down. And then they try to bring up another one. Then, so I think I've forgotten the question you also asked now. I also wanted to say a little bit about that.
So it wasn't a question per se, but more an understanding of overlay networks. Like, what do you understand by that?
All right. So basically, it's just like the way it is in networking, where there are routers or which are sort of a middleman between two networks. So you have like nodes which have their own fan out, but some of these nodes which are found out to have an overlay with other nodes, which so I think a way to think of it is sort of like a network. So there are connected nodes, and then there's also another network of connected nodes, maybe 3 nodes each. But let's say we have P1 up to P6, and then we have 3 nodes in the first group, P1 to P3, and then we have under 3 in the second group, P4 to P6. So, but P3 in this case, or P4, any of them can be in the 2 networks. So you have maybe one particular group having 4, but maybe P4 is in the both of them. I don't know if that makes sense, but basically there is an overlay between the fan outs. So one node can be in like 2 different fan outs. That makes sense. So if a message is sent from a particular node to its own fan out, and then maybe P4 now sends to its own network. So it's sort of disseminated like that. Because one is in 2, it receives a message and then it sends to its own network too, and then everybody should get it. That way it's going to get to everybody in the system, even though the message doesn't send out to everybody directly. Does that make sense?
So I stopped following at some point. Can you like re-summarize like what you just said?
Okay, so let me use an example. So
Okay.
let's say we have nodes, I'm naming the nodes P1 up to P5, and then we have the way the overlay networks work is that you have like a network of nodes which have their fan outs, like you explained earlier. The fan outs is basically the number of nodes it can issue, or it sends messages to. It sends messages to. So let's say P1 to P3 is the first network, let's call it group A. So P1 to P3, they send messages to themselves. So in the case of failure or whatever, they would disseminate information to themselves. But then the second network, which is group 2, calling it group 2, is also, P3 is also part of that network. So you have P3 to P5 as also part of that network. So P3 is the overlay between the 2 networks. So when a message is sent, let's say P1 receives a message and then it sends it to the 3 nodes in its own network, which is P1 to P3. and then P3 receives that message. It also sends it to the nodes in its own network. So, but P3 now is sending to both P3 to P5, and then the other ones P1 to P3. So because of that overlay, it's able to send messages to everyone without having, so P1 doesn't have to send to from P1 to P5. It just sends from P1 to P3, but P3 now does more dissemination.
Yeah,
That makes sense.
That makes sense to me. Yeah. Thank you. So just to kind of give the reasoning behind this, right? So if you have a like in gossip, you just try to send to like a random group of people, right? So you have, I think we said this was tunable with fan out. So you try to send to like a random number of nodes determined by some probabilistic algorithm. And one downside of gossip is that you have a lot of redundant messages, right? So one node can receive multiple messages, multiple of the same messages. But we also want some redundancy because it helps if a node randomly fails, right? So a node to like a particular, so let's say I want to get a node, then a node in the middle on the way to that node I want to get to fails. It will not be able to send messages again. But one of the advantages of gossip's redundancy, message delivery redundancy, message redundancy, is that because it sends to multiple nodes, there might be multiple ways that the message can reach that node that I actually want to reach, right? And so this node that failed would not really matter in the grand scheme of things, because like the message I still want to deliver to all the nodes will get to the nodes somehow, like in an ideal scenario. So while we want to reduce redundancy, we also do not want to completely eliminate it. So the overlay networks is like a compromise. And so we have like this cluster of nodes, or this cluster of nodes, and then we form connections over those cluster of nodes. So what Ugochukwu was saying about, one node kind of being the connector between two groups of nodes, that is the idea, right? So you have like this cluster, you just like form connections, like you form so when the book says form a temporary fixed topology, it's like form like specific connections between nodes so that messages get to those nodes, and then from those nodes, I guess like they can be delivered to like all the others around them, right? So in that way, you are reducing the number of redundant messages you need to deliver, or that will be delivered in the system, but you still get some of the benefits of like the robustness, because the idea is that the node you pick will be like strategic nodes that still help you like achieve that reliability. Like, so if one of those nodes fail, it shouldn't like break down the system completely. So that was my understanding from the section. And I don't know, I hope it's clearer with both our explanations. And I guess the other thing that wasn't clear was, why is it a downside for having interconnected islands with strong preferences towards each other? So strong preferences towards each other is vague. It's kind of vague in this book, but I can imagine like a situation where I pick nodes in my island, like so in my group, based on something like latency, or like, I don't know, there's something that makes me prefer, or makes a node prefer another node. Like a node preferring another node might not necessarily mean that that is the most efficient way to set up the topology to send out messages throughout the cluster. So like my takeaway from that was just that how a node chooses other nodes would kind of be dependent on what the algorithm is, the probabilistic algorithm or the deterministic one, like whatever they decide, the implementation detail. But you just need to be careful so that the choices nodes are making, right? So I can imagine like a probabilistic scenario where like nodes will continue to optimize for, like for example, nodes that they have like I can reach, if it can reach like another node in the lowest with the lowest cost, it might continue to optimize nodes that if say for example the factor that I'm considering is lowest like distance cost or something, it might continue to optimize the nodes that it can reach in the like with the least amount of cost or least cost. And that doesn't necessarily translate to us getting the benefit of the overlay network. So if a node picks another node because it can reach it in lowest cost, that does not mean that that is the best way for us to set up our overlay network. So that was kind of my takeaway from that. I might be wrong, but yeah, that was my understanding. So yeah.
So I just want to elaborate a little bit on that point. I think the overlay network thing, if my thought process is right, wouldn't really work if there are no preferences. So if not, you wouldn't know which nodes are in a particular group because the fan out is limited. And if it was totally based off a random probability that's just trying to get to any particular node in the network, if there are no preferences, there wouldn't be sort of a way to interconnect them. That makes sense. I think the word is vague, but you might have to select nodes based on maybe the network or whatever, but there would be some sort of preferences and also a way to ensure that all the networks or groups are interconnected. Because if they are not, the message would effectively not get to everybody. So I think that's why there is need for that sort of preference, so that they may.
Needed. I think it's just you just need to be conscious that the preferences each node has gives you the best like the best overlay network you need for your cluster. Like because a node I'm picking is closest to me does not mean that that is the right overlay network for my cluster. Like at least that's my thinking. I mean, I haven't thought about this too much. Like I haven't like read any experiments or anything, but like I can just imagine like because I'm choosing, if I think about like greedy algorithms, right? Like the idea is that I am choosing the next best thing I can see right now. That works in some scenarios, but there are scenarios where like if you make greedy choices, you're not going to get an optimal solution at the end. So if like you're always making decisions based on your preferences, it is possible that the overlay network that eventually gets created is not the optimal network for that cluster or whatever. Like, yeah.
Oh, all right. I understand now. Thank you.
But yeah, this is definitely a question we should ask the author. So please let us like pin it. We would have a call with him in a few weeks. Thank you. All right, Amaka, you can continue.
Oh yeah, sorry, I also caught up in discussion. Yes, so next slide, please. Yes, so how I'm interpreting this partial views, it was a little bit, I found it a little bit complex, but how I interpreted it is, so the more like has the number of pairs in a cluster grows, right? There is a problem of distance, right? And not being able to, and for pairs not being able to communicate directly or properly with other pairs, right? So this particular, for partial views, right, it's a gossip protocol that uses a pair sampling service to optimize for message delivery amongst all the pairs in a cluster. So there is the hybrid partial view, right? An extension of partial view. So the hybrid partial view maintains two types of views, right? There is the active view, right, where pairs that are very connected, where they are, right? And then there is a passive view where, sorry, I'm trying to gather my thoughts together on this. Okay, so the active views, right? Active views. Sorry, this is a bit confusing for me.
Okay, I can try to explain. So if you think about the internet, right? So we have switches, we have routers, so on and so forth. Like a switch cannot know about every other switch on the internet. Like, I mean, I guess theoretically it's possible, but that would probably mean like a very slow network. Like if a switch has a list of all the switches like on the internet, I don't know how many that would be, probably billions or something. And it's whatever algorithm is running on the switch, it needs to take into account all of those other switches. That would probably be like really slow. But even apart from like slowness, it's just hard. Like, I don't know, like you just can't know all the other switches. Like if, especially if like you can't reach them, or I don't know. Anyway, let's just say on the internet, every switch, for example, will not know about every other switch. And so by default, like every switch only has a partial view of the internet, of all the other switches on the internet. So whatever like algorithm like we're implementing, so if you like read about algorithms that switches use, like spanning tree protocol, or routers use like distance vector, they implement it in a distributed way because the assumption is that every node doesn't know about every other node, or every other node. And so partial view, I feel like it's just an extension of like all the things we've been talking about. Every node only has a partial view of the network. So it only knows a particular group of nodes. And like at the beginning of this part of the book, like the portion of the book, it talks about how if like a node has a few view of the cluster, it can get very expensive and impractical. Especially if how we spoke about gossip protocols are great for clusters where like the nodes join and leave frequently, right? So the reason why that is beneficial, we've talked about it. If you have a coordinator, you need to register the register. That has like a high overhead. But if we have like a full view, like every node has a full view of every other node, we still get this problem of, because for every node to have a full view of every other node, the registration needs to happen. Like somehow I need to find out about this node that is either here or has left. So whatever like I implement to decide that, if every single node is always going to need to do that every time another node leaves or a node joins, that becomes very like hectic, right? So for efficiency purposes, for cost purposes, partial view is important. All right. And so how do you choose like what nodes should be in another node's partial view, right? So I think that's where like we begin this this part of the book. And then it talks about a peer sampling service. Again, I don't really know how this is implemented, but on a high level for me, it's just this service is just picking nodes or pairs that another node should know about. And these pairs, or these nodes that a node should know about, are constantly updated. Ugochukwu.
Sorry, you can continue. I was just raising my hand so that when you're done, I could see. I think you should finish your thought process.
Okay, thank you. And so they're constantly updated, right? So that is what the, peer service or peer sampling service in the book was talking about. So I don't really know how that's implemented, but all that we know is that this group of nodes are refreshed. And it also connects to the idea from before where we said that you choose in a gossip protocol the nodes you will send messages to, like the nodes in your fan out, range based on probability, some probabilistic algorithm, right? So it still kind of fits into that big picture. And then we now move to this idea of like hybrid partial view. And this is just a big name for saying, so instead of having just one set of, like, instead of saying that I have a group of nodes that's in my partial view, hybrid is now there are two sets of nodes in my partial view. There is one that is probably smaller. So these are a smaller group of nodes that if I want to send a message to, I send to this small group of nodes. And if one of the nodes in that small group of nodes, which they call active in the book, if one of them fails, I can take one from the second group, which is like a bigger secondary group. So I'll take one from that group and put it and replace the one that failed in my smaller active one. And so, yeah, so I would, every time I have a message to send, I would send to this smaller group. And somehow that smaller group will send messages to people or other nodes, and eventually the messages will reach the whole cluster. So that is like my understanding, at least from reading.
Okay, so I just wanted to add something. The partial views, aside from the smaller group of nodes, it's just I think similar. I was trying to figure out the difference between it and the overlay networks. They're very similar. It has a group of nodes which it communicates with frequently, but it also has a larger group, like you mentioned, which it uses for other reasons. So for disseminating information, maybe sending messages, or updating when there are new messages, it uses the smaller group, but also in as much as knowing all the nodes, each node knowing each other, and being able to discourse is sometimes can get expensive in like larger systems. It also has its own advantages like reliability. So it would be able to know easily if a node goes down because every other node is talking to it. So it uses that for other reasons like reliability or basically quick recovery in cases of maybe the entire system fails or something difficult to resolve happens within a small group. It can talk with other ones because it maintains like a passive view, which is basically a larger view of the system. And also because it maintains that larger view, it's also easier for it to send messages that don't just it's also better if you send to the entire system. I was reading something online about it also helping to, there are messages which you want the entire system to know as soon as possible. It might not really be only the nodes which are close to you that need to know it. Maybe more general messages. We also learned about quorums in our last chapter where we discussed some database systems require a particular number of nodes to accept new information for it to be recorded. So I think it would also help with that because now that I think about it, maybe the ones in your active view should be enough to do that if you want to implement that. But maybe in cases where you're changing something like the schema, which is not just related to you, maybe you want everybody in the system to be sure that they know. You could also use the passive view. And then let's add something else, but skip my mind. I'll bring it up if I remember.
Sure, thank you. Maka, you can continue. Are we at the end? I think we're almost. Yeah.
Yeah, I think that's the end of the slide.
This was the final one, or have we talked about this already? Oh yeah, I think
you covered some of it.
we kind of have. All right. Before we go, I mean, does anyone have any questions from when they were reading the book? Anything that was confusing? Sorry, the chapter, not the whole book. Something I found really cool. That one's like, so something I found really cool was this bitmap version vectors. I wonder if like anyone found it difficult to understand or interesting or whatever. Tamia, your question.
Yeah, I was just trying to get like a summary of the chapter. So it's anti-entropy, trying to like see like a divergence between different let's say replicas, for example, in a network. And then these are like the different ways we can identify those divergences. But does he also talk about how they can be resolved, or this is more about identifying them?
Yeah, I think it mostly focuses on ways to identify and like execute the algorithm when you have decided it. So if like you have divergent nodes, and how do you make sure, like how do you like quickly get to or remove the divergence? So how do you detect that something was divergent? So there was the read repair thing. They didn't actually talk about the repair itself, but they talk about how when you're reading, you can compare reads from two clusters and check if they don't match. And if they don't match, fix the one that doesn't match. So either by copying from the more updated node or maybe another way. That would be an implementation detail. So they don't actually talk about how you would implement the fix, but the fact that you need to fix it. And I think maybe the simplest way is like if one node is more updated than the other, then just it talks about ways to identify it. So the two reads, two writes. So when you read, you can detect the differences. The digest read is okay. Like another way of detecting differences with, I guess, smaller footprint. So with hashes, you can compare like hashes together, and if like the hashes are not the same, then you can now request the full data and then decide how you want to fix it. Hint and handoff, kind of the same idea. Merkle tree is comparing hashes in like a tree structure. So I think like these ideas will be part of the ways you implement the overall algorithm, but like how you actually resolve it would be an implementation detail, I think. Bitmap, also the same thing. You're storing like, different versions from different nodes based on some counters. If data is missing in the counters, like that you need to get, states from another node, and so on. I don't know if that answers or if that's more confusing, but yeah.
Yeah, it makes sense. It makes sense. Yeah, just thinking about it, studying Bitcoin actually helps understand many of these concepts because I remember there were Merkle trees are used there as well.
Yeah.
Like as a lightweight to just check if like your data still as a node, and then so you don't have to always do like a full sync, and then you do a full sync when you detect that difference. So yeah, that makes sense. Thanks.
Thank you. Amaka.
Yes, sir. I have a question for Dami. When you worked in Merkle trees, did you have to implement them?
Oh, I didn't work like I was just studying like Bitcoin. I read the book on it, and I looked at some source code. But I think most of those things have been implemented, at least in that network.
Okay. All right.
All right, cool. Yes, Ugo.
Okay, so I have a question. It's not really from this chapter. I was wondering about databases. When we were reading about persistence, I think, and how the data is eventually stored and organized like in the database disk, in the operating system and in the disk of the wherever it's stored in. But I was wondering, I didn't know like specific. I know there are preferred databases, preferred OSs for particular databases, but hasn't there been like an attempt to like build an OS specifically for databases? So instead of trying to maybe fix a flag, fix maybe storing it directly in the database or making sure it's actually saved in the database without going through the memcache with an O direct flag, maybe there is a particular operating system built specifically for databases so that it should help at least resolve a good percentage of the issues we have with building database systems on top of operating systems.
Sorry, is your question that sorry, Dami, you can go.
Well, I was just about to say, so the CMU course that was shared on the channel or the group, I don't know if he's a professor, he gave the reason why. He said there have been attempts to do this, and he gave the reason, but I can't remember exactly. So I would look for that particular lecture and share as well. Yeah.
All right, thank you.
All right, cool. Well, thank you, Amaka, for your presentation and your time. Thanks everyone for joining. See you next week. Bye.
Yeah, thank you too. Bye, guys.